had an event last week, so not expecting you to have done the homework, but if you can just have a quick go, bang out some bullet points for this foundation example if you could, and then we'll have a look at what we're hitting. Okay? Don't worry about the higher one.
Okay.
Don't worry about this higher one. It would take too long because obviously it'll need more detail. Just have a quick go at this to get us started.
I did the high one for the homework you gave me.
Yeah, that's fine. Like I say, we did say at the time it was like, you know, have a go and sort of challenge. I'll have a quick look through that with you. What I might do, just because it's a little bit of a unique circumstance, is perhaps near the end, if I just go back to the scheme, give you a screen capture, just so you can have a look through in more detail.
Okay.
Yeah, or grab it as we go to it on the next slide, just so you can sort of check through that in more detail yourself, if that's okay. Just because we're in a bit of an odd one. Normally, everybody would be able to go through it together.
Okay.
Come on, this does feel like a big class this evening. Although it's unfair to compare to last week. 1, 2, 3, 4, 5. Okay. Right, while you guys are working on that, let me just make a quick note of who's here. 7, Pavel, Yusuf, Sana, and Brian is back in. Awesome. Okay. Right, that's my little register sorted. How are we doing, guys? All got a couple of points?
Yeah.
Yeah.
Yeah, good. Pravin?
Yeah. Do you know for the question is you know for the foundation, isn't that so? That's 2 questions, right?
So yeah, first, so you got describing the arrangement and movement of the particles. Yeah, first sentence is effectively 1 question, then explaining what happens to the particles in liquid during boiling. So you could almost look at that as maybe a 3-mark split, couldn't you?
Yeah. Okay, I was just wondering. Okay, thank you.
Yeah, like I say, I'm hoping it's a good question, and it's important for exam technique, especially when you've got this big block of marks. It is good practice to look at the question, and as you've done there, effectively think, well, how do I break this down? Yeah, it's a good way to approach it. Okay, so let's get some ideas then. So we'll start at the top. Zephan, give me a point, something that would get you a mark, and we'll just rattle through the list and see if we can each try and score one of these 6 marks. Give me something that would score us a mark here.
Should I say for solid?
Anything you like, mate. Anything that would, you reckon, just something that would score you a mark on this, and then we'll move down the list.
Okay. So in a solid, the particles are in a rigid structure and they are vibrating on the spot.
Okay, brilliant. Brian, give me something else that would get us a mark here.
For gases, there are no forces acting between the particles.
Yep, okay. Yes, they're much more spaced out. They're not being held together between our particles. Pravin, give me something else that might get us a mark.
Oh, I wrote about explain what happens to the particles in the liquid during boiling. I didn't get around to that one.
Hey, that's fine. It's all part of the question. We're just trying to see how we would hit. Let's go for it.
I said boiling applies heat to the state of matter to the particles. This application of heat causes particles to vibrate and consequently collide as a result of each of the particles having more energy.
Okay, yep. That's good. That's good. Yeah, we'll have a look at the scheme. I reckon you can probably condense that, but I like what you're thinking. I like we're getting that explanation in, and it is an explain key word, so it's good you're thinking that direction. Sana, have you got audio? I know we've had some issues with the audio connection, so don't worry if not, as long as you can follow along. Okay, possibly not. Do use the chat if you've got a question, okay? So as long as you can follow it, that's fine. If there's anything that confuses you, let me know. I've got the chat window up. Yusuf, Give me something that might get us a mark here.
Is it the fact that when a liquid is during the process of boiling a liquid, the intermolecular bonds are being broken to change it into a gas?
Yes. Were you here for me prattling on about kettles?
Yes.
Yes. Hey, if you remember it, then I'm going to keep it. So yes, it's the idea of the forces between our molecules are being broken down. So as Brian says, then when you get to a gas, and this is how this question, as Pravin's pointing out, it's kind of two parts, but we can see how they're linking ideas, can't we? So we can see the two kind of topics that we've studied and how this one question is trying to link them all together. All right, and that's basically what our 6-mark questions are going to be doing. They're going to want to try and get you to connect things that you may have done in different lessons and learned as different topics, but they do follow on or they do relate to one another. Let's have a quick look at the mark scheme, and you'll see why I didn't set you the higher one just as an introduction to the lesson here. So the way we can break this down, let's just inflate this a little bit. So with foundation, we're looking for relatively simple points, but there's no harm in us sort of extrapolating out, because what if we're sitting a higher paper and they ask a very similar question? It's not impossible. So we've got this idea: particles are solid, they're very close together, regularly arranged, and Zephan added that they've got that vibration on the spot or in a fixed position. I think they'd allow you kind of on the spot or either. So yeah, we've covered that there with the description. Liquids. We didn't necessarily say this, but I think in Brian and Pravin, when you're discussing the state change, you started to hit on this, the idea of them being closer together but moving more, and then in a gas, very far apart. So we mentioned the idea that there's no molecular force there because they are far apart, and they're bouncing around randomly. So they've been asked to describe the movement. Yeah. So in a liquid, we've got them flowing, they're moving randomly around, and in a gas, they are very far apart, and we've still got that random movement. So then how have they defined our boiling? So during our boiling, we transfer energy to the particles. That's good. We touched on that. We've hit that idea that as we're adding energy into our system, we're transferring that energy to our particles, to our molecules or our atoms, or depending on what our substance is made of. And it's breaking the forces of attraction, or the intermolecular forces are overcome and broken down, and that is what allows us to go from this fixed regular structure then to our close but random and flowing, and then eventually to be completely separated to enter gaseous state. So that's good. Yeah, and I think we've added a little more detail obviously than foundation might have gone into in our answers, because we are trying to look at a higher level of answer. But yeah, key points there that we've identified really well. And also just that basic bit of exam technique that had 2 key words in it, didn't it? It had a describe and a second part, explain. And so when you look at the marks, you can think, all right, so there's 3 descriptions to do and 3 components of my explanation. Might be a way to split it. Or if you get stuck and think, oh, I can't really think of any more to say on an explanation, I think I've hit it. Well, maybe just add in a little more detail on description. So it's worth bearing that in mind. Oh, Zephan, let me just scrub that out of the way. And just for your reference, because I know you had sort of sat and done them both, that's the recommended scheme. Goodness me. That's the scheme for the higher. So that's the kind of bullet point summary of what's recommended there. Similar concepts, but that was using that little table of data, wasn't it, to draw a conclusion and to extrapolate out. But it's all this idea of the relative strengths of atomic bonds and intermolecular bonds, how easy it is to overcome them, break them, just at that higher level, because it's asking you to interpret a table. You okay with that? Have you captured that? Yeah?
Yeah.
Obviously, if you have any questions about that, so if you've had a look over it by next session, obviously just ask me and we can go over it. Okay then, guys. So that's given us a little bit of a chance to look at what we had. What we're going to start then, the sort of topic within this unit, because last session I did like a little bit of a topic test, so I'm sure everyone's heartbroken that they missed the test. But I just sort of wanted to sort of summarize and catch up, because we've covered 2 units worth of AQA stuff. So I just wanted to make sure that I was sort of explaining things properly, and that you guys were able to remember it. So Zefan's one of our younger students, and he seemed to be all right with it. So hopefully we'll be okay. We want to move on to quantitative chemistry, which is essentially the maths behind chemistry. So when you see your chemical equations, that is the quantitative aspect of chemistry. How much of a substance are we dealing with? Either how much do we have, or how much is produced or used in a reaction. This is where we're going. And to start off, we need to kind of call back to what we did way back in the beginning, looking at the use of the periodic table. So just to be sure, do you guys all have a periodic table for reference here?
Yeah.
Because you'll need one.
Yeah.
Either in the tab or in your books or whatever you've got. As long as you've got it for reference, we're going to call back to something that we did on that. So let's dig in. We have discussed this idea when we were talking about the periodic table, relative atomic mass, haven't we? Which number is that? We've got two numbers on our period. Say we're looking at an element. Which one do we know is the mass?
Top.
I know where you say that, but periodic tables can be laid out differently. So
The larger one.
The larger one. That's what I'm looking for. You're not wrong. You might be looking at the periodic table where it is on the top. But as Brian says, you look for the larger number is going to be the mass number. And why is that, Brian? Why do we know that must be mass?
Because if I remember correctly, the mass number is the amount of protons plus neutrons. So it's obviously going to be larger than the proton number.
You both remember correctly and read correctly. Yes, it must be the larger, mustn't it? Because the other number tells us how many protons and how many electrons we have. So the mass, because it's also including neutrons, it must always be the larger number. All right, so just remember that's specifically what you're looking for in case you see a periodic table with a slightly different format. Now, this is why we have this rather strange term of relative mass. The reason we say relative mass is because it isn't the actual. It is a kind of a compromise. It's an easy way of expressing the mass so that we don't have to deal with the actual mass. And this is the reason why. If you've got an atom of carbon here, this is the actual mass. Now, I don't know about you, but even in standard form of using 10 to the minus 23, I don't want to have to keep writing that out when I'm doing my equations, which is why we had to find a way to simplify. And so we end up with a mass that is relative to other atoms. Okay, so we know that if magnesium with a mass of 24, we know that's twice the size relatively, it's twice as heavy as a carbon atom. All right. And we remember in my little banner here, our isotopes, this number, when we look at it on the periodic table, is an average of our isotopes. Yeah, do we remember discussing all this? Same number of protons, different number of neutrons?
Yeah.
Yeah. And we did a couple of exercises where, again, it's a question they can ask you is, if these are the isotopes, what is the relative atomic mass on the table? And we worked those through. So,
I don't get what isotope.
The isotopes. The isotope is say you've got carbon 13. So it's an atom of carbon, but it has a relative mass of 13 and not 12. If we think back to our original work on the periodic table, I can't remember whether you were with us at the very beginning, Pravin. But when we're looking at, I think you joined in a little later. Okay, so an isotope of an element, it's the same element, but it has a slightly different mass number because it's got a different number of neutrons in its nucleus. So carbon 13 has one extra neutron. Okay, so there's slightly different states that certain elements can exist. So when we look at them on the periodic table, for a start, the one you see on the periodic table will usually refer to the most common form known. But your mass, if it's not a whole number, that definitely indicates that they've averaged the most common isotopes out. So I think carbon is carbon 12, carbon 13, and carbon 14. I'd have to look that up to be exactly certain which ones they take. So they look at they'll use the different isotopes and say, well, on average, then the relative mass is, and that's what you will see in most periodic tables, is the kind of the average of all the different forms of the element to try and account for that. Does that make sense?
Yeah.
Yeah. I might have to revisit the structure very briefly in a later one just to try and make a bit more sense of that. So, so if that's our relative atomic mass for a given atom of an element, we also have what's called the relative formula mass. We've talked about our chemical formulas for molecules and for substances, and yeah, essentially, if you take the relative mass of each atom in a molecule, and you add them up, well, you have the overall relative mass of that molecule. Fair? So if we look at water, there's 2 hydrogens and an oxygen. Each hydrogen has a relative mass of 1. We've got 2 of those, plus the oxygen's relative mass 16 for an atom. So that molecule adds up to a total of 18. Nice and easy, isn't it? With a nice small molecule, anyway. Yeah. So that's the difference between your AR, your atomic relative mass. I think it's awkward they phrase it that way, but your atomic relative mass, and your formula mass, or I don't know, maybe you could think of that M, your molecular relative mass. Okay, it's basically the same thing. So for a molecule, look at its formula, total of the mass. Right. Have a quick go at those then. Given those molecules, given these formulae, and given these ARs, atomic relative masses, give me the MRs, please. Have a quick scribble down.
Okay, I'm done.
Cool. I know it's a bit odd, guys. Do let me know when you're happy to move on, because obviously I can't see when you're finished. So Zephyr, hopefully some of the stuff we did a little while ago with algebra is coming useful here for manipulating things around and substituting.
Yeah.
Because I mean that's essentially what we're doing when we're looking at this kind of calculation.
Yeah. So it's magnesium, and then it's nitrogen and oxygen. So it's 3 oxygens, and so it's 2 times by the nitrogens and 3 oxygens.
Where are we looking? Down here. So yeah, in fact, I think Pravin just put something up. So this means there are 2 of whatever is in the brackets.
Yeah, that's what I'm saying.
Yeah, 2 of what. So this is a group,
Oh,
and 2 of those groups in that molecule.
Yeah.
Yeah. So obviously each formula is for a single molecule, but within that single molecule, there are 2 OH groups, and or down here there are 2 NO3 groups. So it just adds a little bit of a step.
Okay.
Are we all right with those?
so for the second question, does it mean there are 6 oxygens?
Yes, because that indicates it. So O3, yep, you're correct. O3, 3 oxygen molecules, but then this complex of NO3, there are 2 of them. So yeah, in total, you'd have 6.
Okay.
So it's just looking at how to break the formula up, get around those kinds of bracket issues, and then just chunking it together and adding it all up. Are we ready to have a look at these? Top one?
Yeah.
Yeah.
Yeah. General yeses?
Yeah.
Oh, I've covered it with the answer from the other one. I wondered what was going on there. There we go. Okay, so this is how we're resolving it. So, ooh, the mouse has gone a bit crazy. So we've got our masses there, or we might have to look them up. It depends how generous they're feeling in an exam. They might expect you to go away and find those. But are we happy with why we've calculated that out this way? Why they've put those where they have? I think they've done that in a little bit of an odd way. I would probably have just worked out that that's a total of 17 and then doubled it. But I mean, yeah, I'm more inclined to have done it that way. But it's whatever makes sense to you. You should come out with the same answer. There's no correct method. You'd probably be asked to show you working for, say, 2 mark or whatever. But don't get too hung up on doing a particular way. As long as it makes sense to you and the logic of your system works, you're getting the right answer, go with what you know. So similarly then with the second one, so we've got the same principle, just slightly bigger numbers. We come out at 148?
Yeah.
Yeah. No surprises?
Yeah.
Good, excellent. So, I mean, these are quite chewy examples, but that's probably as difficult as that kind of question is going to get, really. All right, some slightly harder ones down here. I tell you what I'll do, just in the interest of time, and I think you have shown you can do that. I'm going to reveal those. I'm going to be a bit mean and ask you to do that very last one. Just because I think we've shown that we can do it, but just try with this larger formula. Just to make sure that we don't make a particular mistake I want to spot for.
What's ammonium?
Ammonium. So ammonium is this component here. So an molecule of ammonium is NH4, and ammonia is NH3, which we looked at in our covalence. So ammonium is a nitrogen with 4 hydrogens attached, and then we've got a sulfate. So we've got a sulfur and an oxygen group on here. I think I might have to put something in on nomenclature later. Just, yeah. I think once we've got this idea of the composition down, then we can get into the strange way that chemists name things, which, as a biologist primarily, I really don't like the way that chemists name things, but we'll have a look at that in a different session. So yeah, this is a little bit mean because I'm asking you to go and look these up, but hopefully you get the idea. So I was going to make it in the table, but to be honest, I think as long as you got those two okay, we've proved the principle there. And if you've done calculating that, just see if you can quickly run these through and match them up. Give you a clue there. So there's the AR values, relative atomic masses.
I'm done.
Excellent, thank you, Yusuf.
Yeah, me too.
Yep.
Yeah, I'm done.
All right, excellent. Let's see. So, 132.
Yeah.
132.1.
Yeah.
Confirmed.
Yeah.
Good. No surprises. Excellent. So you see, even with a larger molecule, it's relatively simple as long as you know where you're looking on your table and you're happy with sorting out the brackets and not getting caught out by them. Okay. Going to leave that one. I kind of want to crack onto this next key concept and make sure that we get it. So, and we're about the halfway point. So this seems like a neat time to move on. All right. How many of you then have come across the idea of moles or molarity?
Sort of.
Sort of.
Not heard of it.
No. It's Brian, being as you're one of our year 10s, I would expect that you've probably heard the term, but it really depends on what order your modules have come in as to whether you'd have covered this one in particular.
I'm actually in year 9.
So, oh, sorry.
I'm moving to year 10.
Yeah, so of course, yeah, there's the transition exams at the end of each one. I get confused. So you may or may not have covered this, but that's why we do these. Is so this can act as a bit of an introduction. And this is, I'm hoping this makes sense because I've had to teach moles and molarity a number of different times to many different students, and it's one of those that I think it either clicks and you just go, oh right, that makes perfect sense, or it takes a little while to get in. So I've tried to sum this up as best I can. So just like we've got our relative masses and the idea that, well, we don't want to be dealing with this awkward 10 to the minus 23 idea, moles are a similar idea in chemistry. They exist to make it easier to do calculations so that we don't have to look at such gigantic amounts of atoms. You think of the number of atoms in any given object, it becomes unwieldy. You don't want to have to calculate with them. Now, the reason we have this nice little way of making things simple is because of this Avogadro, this very special number, this special constant that was discovered. What we're saying is, if we have 6.02 times 10 to the 23 atoms of carbon, that will have an actual mass of 12 grams. Its relative atomic mass is 12. we've sort of said that's almost an arbitrary thing. That's sort of relative. But this was discovered to be a constant universal truth, which is why we can keep using our relative atomic masses. Why we assume that protons and neutrons are essentially worth 1. It's part of why we discount electrons from the mass. But this little coincidence, this happy little coincidence, this number of atoms making an actual mass in grams, the same as the relative mass, allows us to do some cool stuff. So when we say we have a mole, so if I say I have 1 mole of carbon, or I have a 1 molar strength acid, or whatever, I'm saying there are Avogadro's number, there are 6.02 times 10 to the 23 atoms of carbon or molecules of the acid or whatever it is. I'm saying it's that number of particles in there. Right? So my examples that I've tried to sort of get it hopefully easy to understand. If I say I've got a pair of something, I mean 2, don't I? Yeah? So I use this 2, but numerically I'm saying 2. If I say I have a dozen of something, numerically I mean I have 12, but we know what the term dozen means. And thus it is that when I say in chemistry I have a mole, I'm saying numerically I have that many.
But you know how when it says that it happens to be that 6.02 times 10 to the 23 of atoms have a mass of 12 grams, how come when they show it on the periodic table, only one has a mass of 12? How come they don't, like, I don't know how to explain it, but...
Why are they not using grams?
No, it's not that. It's like it says that you need 6.02 times 10 to the 23 of atoms of carbon to have a mass of 12 grams. But I don't really know how to explain it. But
it's just something that it's just a fact that they've discovered. And if you have Avogadro's number of an atom, then the actual weight of the substance you have will be more or less equal to its relative mass. So its relative mass obviously doesn't have units. They're kind of arbitrary. But because of this little coincidence, it means that, say, if it comes into concentration, we'll move on to that probably next time. But to try and explain it is, if someone says to me they want a 1 molar solution of copper sulfate, you know, the blue, that nice blue liquid.
yeah.
Do an experiment. I want a 1 molar copper sulfate solution. When we're talking concentrations, what I need is 1 mole mass. So I need X number of, I need the grams for 1 mole, and I need to add that into a litre of water. That's how I know I've got 1 molar solution. So to do that, I can find the MR, because I'm talking about a molecule there, of copper sulfate, so we've got a compound, a molecule. I can add up its MR, convert that to grams, weigh that number of grams, mix it into, make up to a litre of solution, and that allows me to say there's 1 mole worth, there's Avogadro's numbers worth of copper sulfate molecules dissolved in that water.
Okay, but then how come? I think I know how to ask that question a little bit better.
Okay.
On the periodic table, the atomic masses are different. Those masses are different because of the fact that not everyone has 6.02 times 10 to the 23. Is that why that all of them are different? Because they have different numbers.
Ah, no, I see what you mean. No, so the relative masses, those are relative to one another. So they take the idea that hydrogen is relatively 1 on its own. And relative to that, a carbon atom is, relatively speaking, 12 times greater. 12 times the mass.
Okay.
But if I had 1 mole of carbon atoms, I have Avogadro's number of carbon. If I have 1 mole of hydrogen, I have Avogadro's number of hydrogen atoms. It's
I see. Okay.
Yeah. This is why I'm trying to explain it with this idea is, I can have a pair, I can have a dozen, I can have a mole. The number it refers to stays the same. So it's
Okay.
a term. It's a term for an amount. Does that make sense to everyone? Like I say, this is one I've often found people either go, "Oh, I get you," or not. So, what are we thinking? Does that make sense the way I've said it?
Yeah.
Yeah.
Yeah. So it's a term to mean that amount. It's a shorthand. So for perspective and to try and get this idea, if I scaled this up from atoms and we use something bigger, if I had that Avogadro's number, if I had that many, a mole's worth, 1 mole of ping pong balls, this is what it would look like. It would cover the entire Earth in a layer of ping pong balls that was 40 kilometers deep. Mount Everest and then some. It's an enormous, enormous quantity. But that is 1 mole of ping pong balls.
Oh.
Have I lost you there, Zevon? We've all gone very quiet. Have I confused that? Have I confused them?
You've mind blown us.
No, seriously though, is that is that quiet because you said what on earth are you on about? Okay, don't worry about it. Type into the chat if you've got a question on it, mate.
If you had a mole of something else, you had a mole of like I don't know, anything else, would how much it covers of the Earth be different because of its relative atomic mass?
Yes.
Oh, okay.
So if we keep the ping pong balls, right? Think of a ping pong ball next to a tennis ball. Right? They are both balls. They are both spheres. The tennis ball is, relatively speaking, what do you reckon? 3 times bigger?
Yeah.
Right? So if our ping pong ball had a relative mass 1, we would say that our tennis ball had a relative mass 4.
3.
It's 4 times larger. Yeah?
So it would cover like a bigger depth.
Yeah, it would cover a much bigger depth. But by saying we've got 1 mole, I would still have the same number, Avogadro's number, of the tennis ball.
It would just cover a bit more of like depth.
It would be maybe 4 times deeper because we're talking about something that, relatively speaking, again, we come back to our relative mass, we're talking about something that is relatively 4 times bigger. You see? I might have to keep that one. That's actually a really good way of doing that. Okay. So, to give you a way of calculating with this, and then I'm hoping to do a couple of examples, but to be honest, even if we have to do those next time and we basically just get the concept across, I think that's more important, because if you don't get this idea at all, and then we start trying to do equations, it all goes completely wrong. So how do we calculate how many moles we have? Well, we can take the mass of grams of a substance that we have, divide it by its MR, of all the elements, say if it's a compound, and that will give us how many moles. So if I have 12 grams of carbon, and we're just going to go with an element, so we don't need to worry about M. So it's AR being 12 grams divided by 12, I've got 1 mole. All right, so this is worth remembering. Feel free to capture that. This is silly, but I thought this was kind of cute. Think of Mr. Mole with a mass on his head, if you're trying to remember. This is in case they don't give you the equation. Again, in higher tier papers, they may not give you the equation. They may expect you to just sort of remember the relationship. So yeah, if that's useful to you, by all means capture it and remember whichever way you want. But that's the simple sort of formula triangle. We love these in science.
Is MR atomic mass?
So the MR is your this is talking about a compound, so this would be your relative formula mass. But if you were talking about a pure element, you could just use the atomic mass, couldn't you? So it depends. If you're if you're given an MR, you're probably talking about a molecule rather than just the atoms. So it's probably multiple atoms joined together. More often than not, you'll be dealing in the MR, so a relative formula for a compound, for a larger molecule.
But
Okay.
at the top where it says how to calculate number of moles, it says mass in grams over mR. So if they didn't give you a compound, you would just use the atomic mass, right?
Well, it is a bit annoying because the terms kind of start to bleed together. But if you've got an element and the element exists as a molecule, right? So say hydrogen is H2, isn't it? It exists naturally as H2.
Yeah.
So you don't get hydrogen floating around as single atoms. It bonds to itself. It forms a diatomic molecule. So I think that really is why they've tried to emphasize MR, so that you don't just, so that basically so you don't get tricked by that. So I think that's why they try and get you to remember the MR first. And then, to be honest, in questioning in tests, they are far more likely to give you something that exists as a molecule.
Okay.
This will be how they ask you for it. But it was important to get the AR so that you understood where the MR was coming from, if you see what I mean.
Okay.
Yeah. So yeah, it's a fair question. And in exams, I would say this is what you want to scribble in the margin somewhere if they don't give it to you. So have a quick go at these. Let's see if we can apply this all together. So given this trend, can you complete for these three substances their relative formula mass for the molecule? So that, again, these are molecules, so an MR, and then convert to get 1 mole of the substance. And then a couple here where you've got to try and use the calculation a little. So I'll give you a minute or two on that. And I'm hoping that as you do these, it will start to come clear. Oh, what is the unit for moles? Yes. If you
something.
units for moles, you can just use. Oh, text is white. That's not very useful. Why has it done that? Rubbish. You just put mole without the E, usually. When I'm putting acids or other solutions out, if that's important, you either use an M, so or you put mole to indicate how strong it is. Like I say, we'll get on to concentrations probably next time now, but it's very similar. Once you can do this, concentrations become much easier to understand. It's taken a little longer, but at least we've definitely covered that. I don't want to move on without having done that. How are we doing? I know these are larger formulae. I think you might have ammonium sulfate from before. Now, it's a small thing, but I'll just point out, I know this is sulfate with an F and this is sulfate with a PH. The standard way to spell it is with an F, but I haven't updated my spell checker on PowerPoint and the squiggly line was annoying me. So I apologise for any confusion on that one, but we do all spell it with an F now. How are we doing with these?
Good, I think.
Mm-hmm. So if I show you these are the MRs, relative moleculars, then it follows it's the same but in grams, yes? And so, if for example we want to know 2 moles, what must we have to do?
You just times the relative formula mass by 2, wouldn't you?
Yep.
Yeah.
And then if they're asking you for how many grams, yeah. Same if you're 1.5, you've got your MR, you know what mass is required for 1 mole, so for half a mole, you simply halve that. So down here, a bit mean because I've asked you to look at one that wasn't in the table there. Anyone got to that one yet?
On that right now.
Okay. Give me a sec. So who's got an MR for me for CuSO4, copper sulfate?
I got 2.56 moles.
Oh, you've gone right. You've gone right to it. 2.56. Why 2.56? What was your starting MR for the molecule?
It was 125, I think.
125.
I think, and then 320 divided by 125.
Okay, so yeah, so we get the mass divided by our MR to give us the number of moles. Do we agree?
Wait, I thought the MR was 151.5.
You reckon 151? All right, why the difference? What's crept in?
Oh, I probably made a mistake.
Have
Because
a look then. So,
doesn't
what have we got?
it have to end in 0.5 because CU is 0.5.
Yeah, if we've got up there, I mean, Brian, if you've got if you've used your periodic table and it's rounded, that's perfectly fine.
Okay.
Or you,
Yeah.
or you could use the value that's up there. If you've got one that's rounded it to whole numbers, that's fine. Or if you've rounded up at the end, that's okay. But why have we got a bit of a difference? So we've got 1 copper, which is.
I know I've done wrong.
Did you miss one?
No, CU, I read on the internet that it was it had a RAM of 29, but actually it has 63.5.
Okay, so that's lowered it down.
Wrong.
So,
Yeah.
Oh, I was
Okay.
wrong as well. I was wrong as well.
And what did you miss?
Oh, I did
Okay.
when I was doing it, I forgot that I did S as 24 instead of 32.
Okay, so that's fine. I mean, this is the first time we're doing it. So have a quick look. Anybody want to amend their estimate?
Is it 2.01?
Oh, you're going to so 2.01. So about 2 mole.
Yeah.
Yeah. It's because your MR came to what?
It came to 159.5.
195.
No, 159.5.
Oh, sorry, 159. 159. Well, if we say that's 160 just for the sake of ease,
Yeah,
right?
it's
One.
roughly.
So we've got roughly double. So we can. So yeah, 2 point something something is fine. Yeah.
Mhm.
Okay. Right. Well, I'm glad we've gotten more comfortable with that. Homework-wise, because we've got about 5 minutes left, I had a couple of things in mind. One, if we manage to get through relatively quick, but I mean, we can always move on next lesson. That's the beauty of doing it in tutorial style. We can break this down and give it the time it needs. So we'll carry on next time and look at how these examples get a little bit more complicated. But homework this week then. I have got a few examples there, but I want to try and get a few more so that you can just do this as a screen capture. That would be a little bit better. I might have to be a bit awkward. If I say grab a capture of 1 to 6, and then I'll scroll it down. I apologise that I'm a bit ignorant of the technology. There's probably a much easier way of doing this that I haven't figured out yet.
You can just go up a space for each one. Don't leave a gap between two.
Yeah, no, I must admit this is just a sheet that I would normally have printed off. So, this is laid out for a photocopier. I'm just wondering if there's a way on GoToMeeting. Is there somewhere that I can sort of upload a file? Do you know, I'm just going to have to sit and muck about with that and figure it out. I'm just going to have to teach myself how to use this more effectively. There must be a better way to do this than just asking me to print screen. But that's my problem, and I'll deal with it. So, you got 1 to 6?
Mhm.
Yep. 7, 8, and 9. So if you could go through that for me, just to make sure that we're comfortable with that, and then next time we will move on to the slightly harder version of this, if you like, which is looking at the relative percentages of mass. So they might say, of the mass of this molecule, how much of it is from the sodium is contributed by sodium, right? We'll have a look at how we move. Sorry, carry on.
Is molecular weight just atomic mass?
So your molecular weight is your MR, your relative molecular weight.
Okay.
Okay. So remember, whether or not you're doing, whether you're finding grams or whether you're finding mole, just make sure that you're using the equation the correct way round, if you like. And hopefully, just doing a couple of these examples and then getting used to doing a kind of combined MR, it'll just get us a little bit faster with looking it up and finding the answers out. And then I think it moves into, yeah, there's just a few more examples. I tell you what, then take 15 to 19 just as a bit of a stretch, where we're getting into looking at moles of compounds. So these are slightly harder ones, slightly higher level, just to give yourselves a bit of a push once you've done those. Comfortable with that? Do we know? Have we got it? Oh, didn't get the first three. Sorry, Yusuf, I'll scroll back up. Has everyone got them?
Yeah.
Okay, so Yusuf wants the first three. Sorry about that, mate. There you go. All right, so we're happy with those. Just to try out a few examples, and then there's those slightly harder ones where we're looking at working with a compound, but it's the same basic principle. So just getting used to using those numbers and manipulating them to get either the grams for a given number of moles or the given number of moles within a set mass in grams. Yeah, it's just getting used to using that triangle. And like I say, then next time we'll go on to the sort of slightly trickier idea of the maths behind it, but hopefully it will make a bit more sense once we've got this pinned down. All right. So I'm glad we've managed to sort that out. Everybody happy with that? Anyone got any other questions about it before I let you go? Because it is now 9, but I'm happy to take it if you've got a question burning there for the homeworks or anything like that.
No.
No? Okie doke. Everybody all right?
Thank you very much.
Yeah.
Excellent. Right. I shall bid you good evening then, gentlemen, and I'll see you next week, and we'll dig a little deeper into this quantitative chemistry.
Okay.
Right.
Bye.
Bye.
Thank you.
Good night now.
Bye.